Hello again. We're starting chapter 8, further applications of integration, and we are only going to look at two sections here, arc length and area of a surface of revolution. So 8.1, arc length. So I'm going to write the distance formula for a quick refresher. The square root of x2 minus x1, everything squared, plus y2 minus y1, everything squared. So let's say we have a function f of x, and we want to determine the distance, the arc length, so on the function between this point with x coordinate A and x coordinate B, so on the closed interval a comma b. Okay, so somewhere we have a generic pi minus 1 point and pi. So as we've done with with the areas and integrals, areas, definite integrals, areas, and volumes, we're going to do the same thing here. The arc length is the limit as n approaches infinity. Now the sum from I equals 1 through n from all these tiny little distances. So this is the distance, pi minus 1, pi. And this, of course, with the limit of the Riemann sum and using the distance formula, etc., we end up getting limit as n approaches infinity from the sum from I equals 1 through n, from the square root, that's why I put it here, 1 plus f prime of x squared, of course, delta x. Well, we know that this is the same with the definite integral, of course, between a and b, from the square root of 1 plus f prime of x, of course, squared dx. As we know, f prime of x can be replaced by dy over dx, so we're going to do that just in case we need that form. 1 plus dy over dx, everything squared, of course, dx. I call a word of caution here, dy over dx or f prime of x must be continuous on the interval a comma b for the fundamental theorem of calculus part 2 to be applicable. Otherwise, we know we're running into an improper integral. Okay, as we've experienced in areas and volumes, we may have to integrate with respect to y, which means the arc length formula will change, let's say from c to d, from the square root of 1 plus dx over dy. So now we are differentiating x with respect to y, of course, squared, and dy. So that is also possible. Now, we also have something called an arc length function given to us in a form of a integral. So this is the integral from a to x, the square root of 1 plus f prime of t squared dt. And applying now the fundamental theorem of calculus part 1, if we want to find the derivative of this, we're going to differentiate the left-hand side, and differentiate the right-hand side. So we get s prime of x, which can be rewritten as ds over dx on the left-hand side. So ds over dx. And on the right-hand side, all we have is 1 plus f prime of x squared. Because we remember from the fundamental of calculus part 1, and this is in chapter 5, when we differentiate an integral, we only get the function back because the differentiation and integration are inverse operations. Another notation here, of course, will be with dy over dx. So ds over dx can be rewritten as 1 plus dy over dx, everything squared. And of course, based on the Pythagorean theorem, we can also write the ds squared equals dx squared plus dy squared, and we can create that triangle to look at. Just keep those in mind. So let's look at a few problems. So they are all on page 565. So let's start with problem 9. on 565, we're given y equals 2/3 x to 3/2. The given interval is 0, 2. Let's do some prep first. As we know, we have to find y prime. So we have 2/3, bring down 3/2 times x to 3/2 minus 1, which is 1/2. So this is 1, so this is basically the square root of x. Okay, I'm on page 3. Okay. So then arc length from 0 to 2, the square root of 1 plus this squared, which is x, dx. I will use a quick substitution. 1 plus x du equals dx. No adjustments needed other than the limits of integration, of course. When x is 0, u is 1. When x is 2, u is 3. And we have u to 1/2 du, which is u to 3/2 over 3/2 from 1 to 3. So here's to 2/3. We plug in 3, which turns out to be 3 the square root of 3, and minus 1. Okay, moving on to 13 on the same page, 565. Okay, this time we're given y equals x to the 3rd over 3 plus 1 over 4x. The given interval is 1, 2. So let's do the preps first. Y prime, 3x squared over 3 plus 1/4 negative 1 over x squared. Remember, we discussed this several times. 1 over x prime is negative 1 over x squared. Okay, so let's rewrite it. Y prime equals x squared minus 1 over 4x squared. Let's do the prep. Let's find y prime squared first. So we get x to the 4th minus 2 times the first times the second. The x's will go away. So minus 1/2 and plus 1 over 16 x to the 4th. Now let's also prepare the 1 plus y prime squared. So that will be the square root of 1 plus all this, x to the 4th minus 1/2 plus 1 over 16 x to the 4th. 1 minus 1/2 will be 1/2. And I hope you notice what happens here. This is nothing else but the same thing, but with plus. So it's this, but with plus instead of minus. So this will be the square root of x squared plus 1 over 4x squared, everything squared, which luckily for us, of course, is x squared plus 1 over 4x squared. So notice that we did not write the integral, but we did all the preps ahead of time. So now we are ready to write the integral, and I think I'm on page 4. Good. So now the arc length between 1 and 2 is the square of this. All these calculations were done. So x squared over 1 over 4x squared dx. So let's see what we get now. Let me move this out of the way now. We don't need it anymore. So we have x to the 3rd over 3 and plus 1/4, again, negative 1 over x, and everything is from 1 to 2. So I have 8/3 minus 1 over 8 minus 1/3 minus 1/4. Let's see what we get at the end. We had 7/3, 8/3 minus 1/3, 7/3, minus 1 over 8 plus 1 over 4. The least common denominator is 24. I need an 8 here, a 3 here, and a 6 here. So 56 minus 3 plus 6. 59 over 24. Good. Let's move on to 17 on 565. We are given y equals natural log of secant x on the interval 0 pi over 4. Good. This is a nice one. Y prime is 1 over secant x times the inner function prime, secant x tangent x. So this is tangent x. Now, under the square root, we have 1 plus y prime squared, but this will be the square root of 1 plus tangent squared, which is the square root of secant squared, which is secant x. Very nice. So then the arc length between 0 and pi over 4 is of secant x dx. We know this formula. We discussed it. We even developed it together. Natural log of secant x plus tangent x from 0 to pi over 4. When we plug in pi over 4 here, we get the square root of 2. And when we plug in pi over 4 here, we get 1. But now when I plug in 0, I get 1 and 0, and natural log 1 is 0. So this is it. Okay, let's look at one more. This is my page 5. Let's look at 19 on 565. 1/3 the square root of y minus 3, and the interval is 1, 9. Of course, this time is 4y. I'm going to work on the function a little bit. It's not a function. On the conic section, or I mean on the non-function if you want. Okay, so 1/3, I will distribute y to 3/2 minus 3y to 1/2. I am going to differentiate, so dx over dy equals 1/3, 3/2 times y to 1/2 minus 3/2 y to negative 1/2. I will factor out 3/2, of course, and I get 1/2 the square root of y minus 1 over the square root of y. I will square this and also determine, or later on add 1. So dx over dy, and take the square root, of course. Squared will be 1/4. First term squared minus 2 times the first times the second, and plus the second term squared. Okay, I will distribute now y over 4. I keep writing 2, but that's just 2. It's not 1, negative 1/2. So that is 2. So 1/4 times negative 2 is negative 1/2 plus 1 over 4y. I'm going to come back and change that. So now this is all squared. It was already squared, and this is it. Good. So now we have the square root of 1 plus all this. So y over 4 minus 1/2 plus 1 over 4y. And we notice that this is y over 4, 1 minus 1/2 is positive 1/2 plus 1 over 4y. And this is exactly the same thing we had here, but with positive. So then this is the square root of y over 2 plus 1 over 2 the square root of y, everything squared, which reduces to, or simplifies to, the square root of y over 2 plus 1 over 2 the square root of y. And is this dry? So I can put a 2 in there? Yes. Good. Finally, we can write the arc length. It was between 1 and 9. It is from the square root of 1 plus the derivative square. We already performed all these calculations. So I have the square root of y over 2 plus 1 over 2 the square root of y, of course, dy. And let's look at page 6. Let me change the color. Okay, page 6. Good. So let's see what we get. Equals. Let me move this up. Good. So we have a 1/2 y to 3/2 over 3/2 plus 1/2 y to 1/2 over 1/2, and this is all between 1 and 9. So we get 1/3 because I flipped 2/3. So y to 3/2, these two go away, plus y to 1/2, and everything from 1 to 9. When I plug in 9, the square root of 9 is 3. 3 cubed is 27, divided by 3 is 9. And then plus 3, and minus 1/3 and minus 1. And let's see. 11 minus 1/3, 32/3. Thank you. I hope this helps.